turn this on so everyone else can see it. Well, good evening and welcome to Kopernik. Let me just make sure my audio is reasonable. I don't talk too loud. Welcome. My name is Drew Desker. I'm the director here at Kopernik, and it's great to see you all here. I know we've also got some people that are coming in from our family STEM hour, and so while we're sort of waiting for them to sort of get settled, just a quick introduction. Again, Kopernik's been here for almost 50 years now, and we are actually one of the better observatories here in the Northeast, but we're also a informal STEM education facility. But it's not just for kids like on a Friday night like tonight. We really promote lifelong learning. And so that's what this among the reasons why this program is here this evening. There seem to be a couple of new faces for me here. So for those that are new, would you raise your hand? Be here for the first time? Great. All right, super. All right, for those who are members, would you raise your hand? All right, it's the other half. Okay, great. So I want to just point out that the people that are members actually have some inside knowledge. Is that how valuable a Kopernik membership can be. Kopernik, again, we're a nonprofit informal STEM education facility. We belong to a group of science centers called the ASTC, Association of Science and Technology Centers. And with a Kopernik membership, we can get into any of those science centers for free. So you could go to the Franklin Institute in Philly. You could go to the Intrepid down in New York City, the MOST up in Syracuse, or even Roberson down in Binghamton. So if you like this kind of place, consider getting a membership. It's one of the things that sort of helps keep the doors open and the staff employed. So again, we really do try to promote lifelong learning. We actually have programs for kids as young as 3 years old, Kopernik Kids, and through programs that again, hopefully will just continue us through our entire life. And it's not necessarily we're going to turn everybody here into a scientist or an engineer, but maybe at least an informed citizen, and maybe making me curious about something. You never know where a seed's going to get planted. One of the programs we do here is called Girl Power Science, and it's a program where we're really trying to promote more women in STEM careers. And so it's typically aimed at, in fact, we just had one just last week where it was called Girl Power Artemis. And Artemis, if you might recall from Greek mythology or Roman mythology, Artemis was the twin sister of Apollo. Now, we remember the Apollo missions going to the moon as is what we did back in the 60s, going to the moon. Well, we're going back to the moon again, but with the Artemis program. This is where we're going to land the first women on the moon. One of these girl power science programs we had, actually we were dealing with we always bring a subject matter expert, a female subject matter expert of some sort, in to talk about the work she does. And so we had an astrophysicist who works at the Goddard Space Flight Center down in Greenbelt, Maryland, talk about the work that she does using satellites to look at carbon dioxide levels and those changes. And then at the end of that video conference, the girls got to ask her questions. And so one of the girls in our class asked her the question, "How did you get interested in astrophysics?" Good question, right? Well, her answer I thought was great. She said, "Well, when I was in college, I was an English major. But my boyfriend was a physics major. We would go from observatory to observatory. I eventually dumped the boyfriend, but I kept the astronomy." She now has her Ph.D. in astrophysics and works at NASA. So you never know where a seed's going to get planted on either in a young person or somebody who maybe is looking for a new career. Yeah, so anyway, part of the, when I'm starting to look for talks here at Kopernik, a lot of times it's just things that I'm personally interested in, and we're just very fortunate to have just a stellar university in town, Binghamton University, and we've been able to draw from the faculty there. And this evening we do in fact have from the psychology department, And she's actually been up. She's talked once before about some of the work that she's done, and now she's going to delve deeper into the brain, as it were. And so we will turn it over to you. I'm actually going to take me a moment to just get the presentation up on. Oh, how you like that? I think it's there. All right. So if you want to just turn on, I'll just make sure that your audio is working. And
all right, it seems to be working.
Let's see. Go ahead and keep talking.
Hello. Hi, everybody. Thank you for having me here, Drew. This is great. I love this program. This is, I love sharing knowledge that I have with everyone in our community. So I'm Dr. Anushree Karkhanis. I'm an assistant professor in the Department of Psychology at Binghamton University. And at Binghamton University, I teach neuroscience classes, and I run an active research lab. And we actually study how adolescent exposure to stress and drug may cause or promote addiction behaviors or behaviors that are related to addiction. That is not what I'm talking about today. I'm going to talk about something different today. I'm actually going to focus on the visual system. And what we're going to do is start with how we see things and end with how we attend to things. So actually seeing things is very different from perceiving things. So perception / attention is very different from just physically having something in your visual field. And so I'm going to try to show you those differences here today. So before...
When you're ready to go to the slide, let me know.
Yep, I'm ready. All right, so before I dive into the actual science of things, let's look at a few images, and I'm going to ask you a few questions about how to describe how you think these other organisms in our world see things. So this is how we see our world. How do you think a dog would see this field? Shades of gray. Okay. Anyone have any other guesses? Right?
I think they'd see the red, but not any other colors.
Not any other colors? Okay. So this is how they actually see it. They actually don't see a lot of red either. It's pretty much a gray washout. So dogs don't really have a good color vision, essentially, right? They can see everything, but it's not a great color vision. All right, so this is how we see things in a particular light setting. How do you think a gecko's vision works?
I think the gecko would see a lot of the bright colors, but not much of the dark colors.
Very good. So they're going to see a lot of the brighter colors that are popping up, right? But not everything else. All right, so here's how we see a snail sitting in some sunlight. How do you think a snail would see things?
I think they'd see mostly shades of gray.
Yeah, you're both right. Not much. Shades of gray, pretty weak. Can't really see anything. Just shapes, maybe, right? Pretty blurry. So this is how we see the world when we're looking at a bird. How do you think a bird sees things?
Like close up. Like if it's really far away, I think they would see it close.
They'll see a close up. Okay, what do you think?
They also will, like some birds have eyes on the side of their head, so they'll have 180 degree vision.
Okay, so a different kind of visual field. Anyone else have any guesses?
I think that the birds would see like all of the colors and be able to see things that far away, maybe that far away, really closer than us.
Okay, have you seen my slides? Right? So birds have really good colorful color vision, and so they actually see more colors than we do. So a couple more. So how about snakes? This is how we see in the dark. We're not really good at seeing things in the dark. Yeah? They'll see infrared? Heat, right? So heat maps?
I think they could be able to see like the heat vision
That's
And I don't think it would be very dark.
right.
That's what I thought.
That's what you were gonna say. Okay, good. So they actually see like a heat map. They actually follow body heat when they go around. So very different vision from the way we have it. So let's talk about what is going on here, right? So I'm going to dive into a little bit of physics of the light. I think some of this was actually talked about in the last week's family hour or here. So what happens is when light goes in through a prism, right, it gets just diffracted. When I mean diffracted, the wavelengths, different wavelengths get spread out, right? And that's where we see like rainbow colors. That's how rainbows actually happen, right? And so moisture in the air actually acts like prism. And so that's why when it rains and you have sunlight right after, you see a rainbow. So that's where that's coming from. All of the white light is actually getting diffracted into different wavelengths. So what we actually see is here. And so this is our visual spectrum that we can actually look at. And the color is defined by the wavelength of photons. Now, photons are small particles, that they're energy particles in the light. And so essentially the wavelength at which these photons are moving with defines what color we see. So the shorter the wavelength, so short wavelengths are violet and blues, whereas longer wavelengths are red. And so if I show you the overall spectrum that we have in our world, that tiny little region is what we actually end up seeing in, like, that's our visual field. That's what we are able to see. So we see wavelengths that are between 400 and 700 nanometers, right? So as long as things fall in that region, we can see them. Anything outside of that goes into ultraviolet or infrared wavelength areas, and we do not actually see those. All right. So essentially what we're seeing, when we see color, we see the light that is reflected back. So everything else gets absorbed, right? And so anytime white light hits a surface, the white light has all of these wavelengths in it. And so what's reflected back is the color that we're going to see. So if it's a black surface, all of the white light that hits that black surface is going to get absorbed, and nothing's going to get reflected back. So we're not going to see any color. That's why we see black. If we see a red surface, we see that the red light is reflected back. That's why we see red, right? And that's why when we look at a plant, the leaves of a plant reflect green light. That's why we see them as green. Flowers may reflect red light, and so that's why we see red. So what happens when you have different colored objects and different colored lighting, right? So it's not a white light, it's a different colored light. So here, so this is an apple, this is a red apple. So this is the same apple that's shown in all of these three conditions, right? So I'm going to go through it one by one. So first, this red apple was kept in a red light. We see it as red because there's only red light present, and that red light is getting reflected back. But if you place this apple in green light, now there is no green in that apple to get reflected, right? And so all of the green light is getting absorbed, and we actually end up, the apple looks black, right? And so if we put it in blue light, it's going to look black too. So what the color that we see really depends on what color is being reflected back to us. All right, so let's see what our eye is actually doing. Actually, before I go into the eye, here's something else. Here's another test for you guys. So on the left-hand side, you see these gray squares, and then there are these gray squares on the image on the right-hand side too. Are these the same shade as this gray, or are these lighter than these squares here?
They're lighter.
How many people say they're lighter?
Well, they are lighter, but I
So you're partially right. You're perceiving them to be lighter, right? but in reality, they're the same shade, right? And so one of the reasons you're perceiving them to be lighter is because they're against a lighter background. So in comparison to this lighter background, this square, I mean, it kind of seems to be not as dark, right? Whereas this is a darker background, and you're going to see them actually more gray than they are. So this is just the same exercise kind of zoomed in, right? And so it's against a whiter background, and this is against a black background. But if you actually connect the two, they're the same exact shade of gray. So what's happening here is that your mind is perceiving colors or shades differently based on the background, and so the background and the foreground combination matters, right? And so brightness is defined by pixels, and what it defines, what it is essentially, it's the number of photons that are per square unit space, right? And so if you have more photons, things are going to look brighter. If you have fewer photons, things are going to look darker. But in essence, what it is taking is also the surrounding area and what's in there, right? So what is happening in the nearby pixels? So the edges, right? So edges will define certain shades, different shades. Motion, if things are moving, they're going to appear to be a different color or different brightness. Not a different color, different brightness than if they were stationary. And form, right? So how are they overall? What is the shape and the form of whatever it is that you're looking at? And all of these things are going to shape your perception of whatever it is that you're seeing. So let's talk about the eye a little bit, right? So there are several things in our eye. There are several parts of our eye that actually help us absorb this visual information that's coming into us, right? So the first thing that the light hits is the cornea. And the cornea is the part of the eye that refracts light. Okay, so that's what's going to spread that light, that white light, into those different wavelengths. Then the light enters essentially through the pupil, and that's the opening. So the pupil is the opening in your iris, right? And so that's right here. And so light is entering the eye through that pupil. And so if there is low light in a room that you're in, your pupil is going to be larger because it needs to allow more light to come in. If you go in a sunny environment or a brightly lit room, your pupil size becomes smaller because now there's so much light out there that you don't want all of that to come in. You'll go blind. And so it becomes smaller and it shrinks.
If I could just interrupt, we actually talk about that here at Kopernik, because when you go out to the domes and you want to take a look at a very dim object, you want as much light coming into your eyes as possible. So that's why when you walk into our domes, you see all those lights are red. The red light doesn't affect your pupils anywhere near as much as the white light. So that's why we have all the red lights here.
Absolutely. And then there are these ciliary muscles, right? And so this is the lens of the eye, right? And so if you look at these little striations on the side, those are called the ciliary muscles, and those adjust to help you focus. So they will change the shape of your lens, and that change in shape of your lens will actually allow you to focus more or less, depending on what it is that you're looking at. Okay. So how do we have binocular vision, right? And like depth vision per se? What helps us do that? Of course, we have two eyes, but so do other animals. But not all animals can actually see depth, and so that's a phenomenon that's very special to humans and some other organisms. So what's interesting about our eyes is that both of our eyes see a part of our visual field together, right? And so there are other parts that only one of our eye can see, right? And so around in our retina, we have receptors that I'm going to talk about in a little bit. But what it is that these receptors that are on the middle portion of our retina see stuff that is in the left-hand side. So if you're kind of standing this way, right? And so the middle portion of your retina on the left-hand side of your body sees information to the left of you. And the middle portion of the right-hand side retina sees information to the right of you. But then the outer areas of each of your retinas see the opposite side, right? So outer area of the right-hand side retina see the left information, and outer side of the left-hand side retina sees the right information. And so that's where that overlap occurs, right? And so that's why whatever you see in front of you, you're able to see depth, and both of your eyes see it. What you see on the side of you, sometimes only one eye can see it. Now, animals that have eyes on the side of their heads, they don't have a lot of binocular vision, meaning there's very little space in their visual fields that both of their eyes can actually see. So that's a pretty neat thing that we have. So I just talked about photoreceptors. I promised I was going to talk about photoreceptors a little bit more. And so this is how our retina looks. There's a blind spot, and I'll talk about that blind spot in a little bit. But we have two different types of photoreceptors. We have rods and we have cones. And so if you look in this picture here, interestingly, this is the back of our retina. And these blue images that you're seeing here, those are our photoreceptors. And so if you look at the rod-like shape, those are the rods, and they help you see in the nighttime. So they're not sensitive to light. Those are the cells in your retina that are working at night and in darkness. And these cone-shaped cells that you're seeing here, those are called the cones. And they actually help you see color, and they're light sensitive. And so they get activated, and they want to go and play with other cells when light is present. Okay? Now what's interesting is that these photoreceptors are sitting at all the way the back of your retina. So when the light comes in, it actually goes through other cell layers before it gets to the rods and the cones. Okay? So these rods and cones are at the very back. Another interesting thing is that this is the center of your retina. So like the fovea part, the main focus part, and there are lots and lots of cones in that area. There are no rods in that area. All of the rods are in the periphery, right, in the peripheral vision part of your eye. So where you focus the most, where your retina is focused the most in the center, you have amazing color vision and amazing acuity. So the more receptors you have, the better accuracy you have in detecting something, right? And so this middle part at 0 degrees is where you have most of your cones and greatest acuity. Now, do you see that blind spot? So that's a region where you don't have any receptors in your retina, and all of us have that. And the reason we don't have any receptors in that area is because that's where our optic nerve exits the eye and goes to our brain. So that's how it's connected to our brain. So if you guys, take your hands out and go forward, at some point you're not going to see your hands. That's your blind spot, essentially, right? So of course you don't see anything behind you, but at some point you're not going to see your hand on the side. So that's the region where your blind spot lies, and that's where your optic nerve is exiting the eye and making a connection to your brain. So I showed you there were tons and tons of cones that were accumulated in that central area, right? And I told you that the cones are actually what detect or help you detect color. What's interesting is we have 3 types of cones. We have cones that detect blue wavelengths, green wavelengths, and red wavelengths. So do you notice on the computer when you go to change colors, you have the RBG values that you put in, right? So, and different combinations of this RBG value will actually give you a range of colors. And so basically what cones or which cone is activated, or what group of cones are activated, and what combination they're activated in will dictate what kind of color you see. And so how many people think that everybody sees the same colors? Great answer. That's why a blue, so what's that color? What's the color of the chairs? What kind of blue?
And 305.
A light dark blue.
Right, I'm probably going to hear a different answer from everybody because everybody perceives that blue to be a slightly different shade than it is, because it depends on your experience, and it depends on exactly what combination of cones are activated in your eye when you actually look at that chair. Okay, and so that happens to all kinds of colors in our lives. So what are these cells in the retina seeing, right? The cells in the retina then go on to our brain. And so what we see at the level of our eye are literally dots. That's it. They're just groups of photons. That's all we see. We don't see structures. We don't see colors. We just see little dots that are here and there. Right? And so some cells will respond to a spot in the center. So cells have these receptive fields. All cells will fire to a particular region that they like. And so they cover a particular area in our environment. And so a dot is what they respond to. And sometimes they will not respond to a dot. They won't like something being in a certain spot in your environment. And so that's when that cell will shut off, right? And so here you're seeing that the cell stops firing. So each of these tick marks is an action potential. So it's like the firing of the cell. So here, when this spot of light is in the center, you see increased activity of this cell. And here you see a decreased activity of this cell because it doesn't like it there. Now there's also the opposite that's available, right? Some cells like stuff in the center of their receptive field, and some cells like something in the surround portion of the receptive field. The main point of this slide, though, is to show that at this point, all our cells are seeing are dots, nothing else. Okay. Now, where does information go from the eye? So from the eye, it's going to go to the brain. And so it goes to this part of the brain right here that's called the thalamus. And so that the thalamus region of the brain is kind of like the relay station. So all of our sensory information, whether it's hearing or seeing or touching, all of that information is going to go through the thalamus. So it goes to that region. So that's it. This is a section of the brain. And so this is that region there. And it's very well structured. And so all of this information from your eye is going into this region over here. And so just like the cells in our retina see dots, the cells in our thalamus also see only dots. So nothing yet, just dots, just spots here and there. That are eventually going to get put together, okay? And so just like the retina cells, some cells will respond to a dot being in the center of their receptive field and then not in the outside, right? So like right here. All right, so what happens after this? So it goes to the thalamus. It's still doing dot formations. Now it's going to go further along in the brain. And so it goes to our visual cortex. And so our visual cortex, this is a flattened out brain. So actually, if I go back, our visual cortex is all the way in the back of our brain here. Okay? So it's called the occipital lobe and it's back here. And so that's where information is going to go next. So that's your primary visual cortex, right? And that's where things go from the thalamus region, which is this part here. So what are the cells seeing here? So this is where things start to get a little interesting about how we're actually seeing our world. So there are three types of maps that are on your visual cortex. One map is a spatial map. And so we call this a topographical map. And what that is that at the very end of your brain, at the pole of your brain, you're seeing what your eye sees in the fovea. As you move forward towards the, front part of the brain, you start to see things that are in your periphery. Okay, so there's a spatial map. It's very well organized. That's covered on the cortex in your brain area, or in the primary brain area. The other things that the V1 neurons, or the primary visual area neurons, can do is distinguish which one of your eyes is seeing whatever it is seeing. So there are these things called ocular dominance columns. And so there is a column of cells that respond to the left eye, and a column of cells that respond to the right eye. And they kind of alternate. They go left, right, left, right, left, right. Right? And so if you look at the images in the brain, this is kind of the columns that you end up seeing. And so here, the blue is the right eye, and the red are inputs from the left eye. Okay? So things are getting differentiated here. And now, interestingly, what's happening is now we see orientation columns. And so by orientation, I mean, is something straight or is it slanting? And so we're seeing, different edges that are either straight or at different angles, right? And so that's also in a very patterned way. And that ends up being in a pinwheel way. So essentially, if you look at this diagram here, the straight is represented by yellow. And then as you go along, the angle of this rod actually changes. So how do we go from dots to a rod, right? I mean, the space makes sense. The ocular dominance column makes sense. But how do we get a rod that we see, right? And so what's happening is that multiple neurons from our thalamus are synapsing or making connections with one neuron in our primary visual cortex. And so when they do that, each dot is kind of getting aligned, one next to the other. And so depending on which neurons actually end up making connection with that neuron in the visual cortex, you're now getting a rod formation, because they're kind of being in line. And it's kind of like this cortical neuron now, or this one here, is like combining information from these other lower order neurons, right? And so structurally, as you go up into the brain, you'll see that this is the kind of formation that's happening. So what happens when something goes wrong, right? So how many of you have heard of amblyopia or lazy eye, right? So a lot of us see that, and sometimes we'll see children wearing eye patches on them, and sometimes children will have to wear that to correct the lazy eye syndrome. And so what that is essentially there's one eye that is not dominant, so there's a dominant eye, and then there's this other eye that doesn't actually do its job. And so if you don't catch this at the critical period, what's going to happen is this is your visual cortex, for example. In A, it shows you how it normally looks. There is an input from the left eye, and then one from the right eye, and then left and the right, and the left and the right. Here, one of the eyes is dominating, and the other is not giving enough information, right? And so that's the kind of thing that happens. So at birth, there is no input. This is something that happens develops after birth. This is experience driven. When both eyes are normal, they're typically developing, you get those striations and those alternating inputs from left and right eye. However, if one of the eyes is occluded or it's closed, you're not going to get equal representation on the cortex. And so that's why people wear patches sometimes, to sort of reorient their brain in a way. And our brain's very plastic. So if you catch these things at the right time, you can actually change how things are looking. So what happens next? So we're in the visual cortex. We got that far. What after that? right? And so after that, our visual stream kind of bifurcates in two different regions. So it goes into the ventral pathway or the downward pathway, and it goes into the dorsal pathway. So let's see what's happening in these different areas. Let's talk about the ventral pathway first. That's the downward pathway. These are the regions of the brain that are going to help us identify objects. And that's why it's called the what pathway. It allows us to say, what is something, right? And so we're kind of in this area here now. So again, the ventral pathway is what we're looking at. And so this is where you start to see concentric circles and shapes. So now shapes start to form. So up until this point, your brain couldn't tell you were looking at a shape. Now it can, right? So you're seeing color. Color is something else you start to see. And so now you're going from the secondary visual area to the fourth visual area. And you're seeing colors and circle. Now into the fourth visual area, you actually see more complex shapes. So you continue to put information together. And so you're seeing a more complex shapes now. And now you can actually identify those shapes as objects, right? And that is something, so that's going from the fourth visual cortex to the inferior temporal cortex. And so here, you can see complex shapes and you can identify them. And these are shaped by learning and experience, okay? So what does that look like to you? Yep, and that's because, culturally we're used to looking at that and seeing a snowman. What about that if I hinted Halloween? Yeah, right? And so it depends on what you've been exposed to that you're going to see or identify an object as something or a bunch of shapes as something, right? And so learning and your experience will shape that. And so this is also where expert recognition comes into play, right? So this is where we learn to identify faces, not just objects. And so these are the areas of the brain that are going to help us recognize and identify things around us. So what happens when something goes wrong, right? So there's a disorder called prosopagnosia, and so that happens when there are lesions of the fusiform gyrus. And so when this happens, it's essentially inability to identify and perceive faces. So basically these individuals cannot see a face as a face. They can recognize people, but they'll use other features like clothing color or somebody's, they can see one facial feature at a time, but not the whole face at once. How are you doing on time, Drew? Okay, can we click on that link? If you don't, it's fine. So we'll just watch like the first.
Make a great impression and save time at work. You should.
Who's that?
No, trying to visualize it with hair. No.
Are you sure you don't recognize that person?
No.
No, give me a hint.
You should know this person.
Give me a hint.
Think about it.
No. First name?
Steve.
No.
It's me.
No.
Really? Yeah.
It's you? I can't believe that. I cannot relate that picture to you at all.
Not at all.
No, not at all.
Really, honestly, that does not.
So you see, this is how they respond. They can't, unless they have other features available to them to actually recognize a person, they can't recognize people. Their vision is fine, but they can't actually recognize them. Do you have a question? There's a spectrum. So any of the brain disorders will have a spectrum because the amount of lesion is going to dictate the, how badly people are affected. No, because once there is cell death in the brain, that cell death isn't going to recover, and so it won't necessarily become better. Now, it could get worse depending on what is the issue. If it's a blood supply issue, then it could potentially get worse over time. That's interesting. That's interesting. It's a thing. It's a common. I mean, it's not common, and thankfully, but it is a rare disorder, but it's a quite an interesting one. So this is of course affecting the ventral pathway that is going at the bottom part of the brain, right? Now, just like there's prosopagnosia, which is face blindness, we also have something called object agnosia. And so that is inability to recognize objects. And so essentially it's, you can perceive an object. So if somebody was shown a flower or rose, they could tell you, and if they were suffering from object agnosia, they could tell you that they're looking at something red, something that smells good, something that has different pieces, but they wouldn't be able to tell you that it is a rose. So it's interesting that they can see things but not actually recognize what the object is. Neither. It's the inability to recognize. They remember what a rose looks like. You can tell them, can you draw a rose for me? And they will draw a rose for you. They can see it, and they can tell you all about it. They can describe it to you, but they can't recognize it as a rose. Okay, so it's a recognition thing. They may or may not be able to do that. That really depends. It depends. It's different person to person.
Would it differ depending upon the
No, I don't think so. And so again, that's the same part. So there's a slightly different. There are two neighboring areas: the area that allows us to recognize faces, and the one that allows us to recognize objects. Now the faces it's kind of interesting. It's faces. We're just good at recognizing faces as human beings because we see them a lot. But this is an area there. So there are car experts, and so they have a car recognizing region in that gyrus. So it's a familiarity thing. All right, so that's in the ventral pathway. So what happens in the dorsal pathway? So let's see what's happening at the top part of the brain here. And so this is where motion comes into play. So remember when we saw those orientation of bars? Now we're going to get even more cells put together from that primary visual cortex. And now those more and more cells are going to come together, and those more and more orientation bars are going to come together. And now we can actually see things moving. So the fifth visual area in our brain allows us to see motion and detect motion. So we can tell what direction things are going in, how fast they're moving, and how just our world essentially moves. If you go more towards, if you go further than primary or the fifth visual area, you end up in what's called a parietal lobe. And the parietal lobe is very interesting. It's one of the most integrative lobes or parts of our brain. And so this is what happens when you have damage to the parietal lobe. All right, so there's a syndrome called the Balint syndrome. And so in this syndrome, there are multiple symptoms appear. So one is people can't orient their hands in a particular way. And so it's like that spatial recognition is sort of gone, and that orientation recognition is gone. So in a typical individual, if you give them something with a slit, and you say, you have to put your hand through this, I mean, a typical individual will be able to do that, right? Orient your hand, you put it in, and you slide it in. We do this all the time when we go shopping, when we have to swipe our cards, our credit cards, and slide our credit cards to pay, right? Someone with a Balin syndrome will have trouble orienting their hand in the right way. And so here's another example where this person oriented in the right way, but put it through a different spot in that slit, right? And so that's one thing that happens. The other issue that they have is that they can't actually look at an environment or a scene in a typical way, like a typical person would. And so if you were shown this image, can you tell me what's going on in here? Like, what are yeah, like I mean, in that picture, I know it's a little hard to see because there are all these fixation lines, but can you just describe that image to me? Right, so yeah, so it's a little difficult to see, but this boy is standing on a stool that's falling. Right, this woman is washing dishes and the water is overflowing from the sink, and so these are things they're really absurd and they're weird. It's like, oh my gosh, what's happening in there, right? And so a typical individual will fixate on things that are going wrong because they seem odd to us, right? But someone with a Balin syndrome will fixate on something completely different. Like it's just that, like, the scene won't make sense to them, and they won't be able to actually go back and forth to things that were actually normal or things that were, kind of odd in that scene, right? And so they have these issues with moving their eyes in a patterned way, and identifying where things are kind of odd in the spatial, in their space that they're given access to. Not really, no. So this is another interesting syndrome. This is called hemispatial neglect, also parietal lobe damage. But this usually happens in one half of the brain, not both. And what's interesting about this is that it's the inability to attend to half of your world. You see it, but you can't perceive it, right? So perception separate from vision. And so this is a part of that dorsal pathway. It's going to the parietal cortex, the posterior part of it, the back part of it. And so here, these are the kind of symptoms you see. So here's a model diagram that was shown to a patient, and he was asked, "Can you draw this?" And so what this patient draws is half the house. So they can't actually complete the image because they don't perceive the other half of the house. So here's another one where a patient was asked to draw a clock. And so they draw a circle because they know that a clock is supposed to be circular. But then when they write the numbers in there, all of the numbers are on one half of it and not the other. Right? And so this probably means that the damage was in the right posterior parietal cortex because they're not writing anything in the left. Okay? And what's really interesting and kind of sad is that, here's another drawing where they're drawing only half of the images, right? It said they will also eat only half of their food. So they can't see when you give them a plate of food, they actually can't perceive food in their entire plate. And so they'll only eat the half that they see, and then someone has to rotate the plate, bring the other half into the visual field that they can actually perceive, and then they'll continue to eat it. So it's very interesting how these are very specific disorders that happen within specific parts of the brain.
And with this particular issue, if you were to cover one eye or the other eye, it would still be the same thing.
Yep.
Wow.
Yep, absolutely. So it's a perception issue. It's an issue with the perception. It's not an issue with the vision. So they can see perfectly fine. All right, so now we're going to do a little test. We're starting to get into the attention part of things now. So play that video and do this task. hopefully this one plays too.
Fuel your greatness with Gatorade's proven formula to help you reach your goals.
The monkey business illusion. Count how many times the players wearing white pass the ball. The correct answer is 16 passes. Did you spot the gorilla?
How many people did?
For people who haven't seen or heard about a video like this before, about half missed the gorilla. If you knew about the gorilla, you probably saw it. But did you notice the curtain changing color or the player on the black team leaving the game? Let's rewind and watch it again. Here comes the gorilla, and there goes a player, and the curtain is changing from red to gold. When you're looking for a gorilla, you often miss other unexpected events. And that's the monkey business illusion.
That's good, thanks. So that was interesting, right? I mean, if you knew about the gorilla, you knew to look for it, right? But then there are other things that you don't notice. And so what's happening there is inattentional bias. So things that you do not attend to, you just entirely miss in your world, right? And so the question is, do we really see everything that's around us? Not really. We miss a lot, right? And this is why eyewitness cases are kind of problematic, because they may not see something that they're not attending to, right? So let's talk about attention for a few minutes. Can you spot the yellow object in that image? And when you do, raise your hand. Pretty easy, right? Because we were looking for one thing that was yellow. There's only one yellow object over there amongst all of the green. Now can you find a square in this image? Very good. Still pretty fast, because now we're looking for a square amongst all of the circles, right? So still pretty easy to do. Can you find a green circle? Takes a bit, right? Because you're... Where is it? Nah, I can't find it. Here, there it is. So you're looking for two things now. Now you're looking for color, a specific color, and you're looking for a specific shape, right? So that you're kind of at the conjuncture of two separate features. And so it becomes a little bit harder to look for. Now find a yellow square. There is no yellow square, that's right, but it took a bit for people to actually say that, right? So you guys kept on looking for it longer. Right, that's right. So you're searching for it longer because you're looking for more things, right? And that object isn't even there. And so what happens is, if you were to look at reaction times, so people actually did this study, and they were looking for reaction times, and on the x-axis here are number of items in the display. So when you're just doing a feature search, when you're looking for one feature, people are pretty fast at looking for things, at looking for objects, because you're attending to only one thing, right? When you do a conjunction search, which is essentially looking for two or more features of an object, it takes you a little bit longer because you're attending to more things at the time. And when you do a search where there is no object, it takes you even longer to come up to a decision, because you keep looking for more and more things, right? And just to make sure that it's not there. And so attention, how many things you're attending to plays a huge role on what your reaction time is going to be. So if you're too distracted, it'll take you longer to complete a task and to identify things. So the question then is, do our neurons really respond to a locus of attention? Like, are our neurons actually paying attention? How many people think our neurons can actually pay attention? So if you were to record from one single neuron and its activity, like, would you actually see, would this neuron actually respond to attention? Okay. All right, so let's see. So this was a study that was done in non-human primates, monkeys essentially. Monkeys are really good at attending to things and doing these tasks. So the red object here is what this particular neuron likes. So neurons have these spatial receptive fields that we've talked about, right? And so this particular neuron likes this object in this orientation. Here, the green object is another one which is in the receptive field of the neuron, but it's not attended to. Okay, so the monkey is asked to attend to this red object while it fixates on a separate point. So it said, look over here and look at that red object that's in the corner over there. Okay? And so experimenters here are recording neural activity or firing of a particular neuron. And so every time you see this increase in activity here, that's the neuron actually firing. Okay? And so when the stimuli are present, when these visual stimuli are present, and it is this particular one that the monkey is asked to attend to, this neuron fires. Okay? If the neuron is asked to attend to a different one, essentially that neuron is not going to fire. So it's basically, with a shift in attention, the neuron's activity actually changes, right? And so what our brain is, or what is happening in our brain, is that the receptive field or the responsivity of our neurons continues to alter and reshape depending on our experience. Okay? And so here, so these are possible, so for example, these are possible stimuli that are available to see. The blue line is the normal response of this neuron, and so it's responding to this particular bar, for example, or in a bell-shaped curve, right? So it responds the most to this straight bar. If you were asked to pay attention to that straight bar, that particular neuron that whoever is recording from is going to actually tune up and start responding to that straight bar more and more and more. Okay? Another way this happens is that the receptive field will shrink, and so if you're asked to attend to something, your neuron will start responding to that thing only and not anything else. And so now you're kind of focusing in your attention. Okay? And then sometimes you can even get your neurons to shift their receptive field and what they're responding to, depending on what you're asked to attend to. Okay? And so basically what it is that your attention can cause a lot of changes. Your overt attention, what you're asked to attend to and what you are attending to, will actually change how and what your neurons are responding to. So you can shape your brain quite a bit. So that's kind of what I had. I'd like to thank you all to listening to me. I hope that was sort of fun to go through. And I'm happy to take any questions.
Do you remember the dress that was on the internet with the white or gold or blue? Is it because those cones or bars, like you were saying, some group of population is predisposed to one type of cone and the other one is different, or what was that?
It's all a perception thing. So it's like what is at the perceptual level, what do you actually perceive or see in it? Yep. No. That was nothing to do with psychology. It's just how people were perceiving things.
Yeah, why don't printers use red, blue, and green ink?
Printers use all kinds of inks.
Printers use magenta, cyan, and yellow.
That's a good question. I actually don't know.
One thing I will say is that, like, when we take color pictures with our telescope, we have a red, a green, and a blue filter, and we compress those. So just maybe the chemistry. Joe, you have a.
It's the difference between subtractive and additive colors. Pigments are subtractive. Cyan, magenta, and yellow, they work much better to create the full spectrum of colors. When you're subtracting colors, because surfaces reflect on certain colors, and additive colors like light, colored lights, function differently. Put them together, and the most efficient trio of colors is
All right,
That's
we do have a question from the those on the live stream. Phil asks, how do we see memories?
How do we see memories? That's an interesting one. So I think that has to do with visualizing what you have seen in the past, I believe. I mean, I don't think you actually like see memories. It's just that your mind is visualizing what you have experienced in the past. So dreams are different. Dreams are very different. They're not always conscious. They're sometimes subconscious. So I actually didn't talk about consciousness in today's lecture, but there's a particular part of our brain, the claustrum is what it's called, and more recent studies are starting to see that the claustrum part of our brain is involved in consciousness, but we don't know about dreams yet.
I know. Yeah,
that's a topic I run away from.
I know that there's some people that have migraines, and they have sort of what they call an aura.
Mm-hmm.
Do you have a sense of what's going on, sort of physiologically, with that aura?
So not entirely, because that's another field that's kind of, it's kind of slowly maturing. But migraines happen as a result of misfiring of neurons in the brain, and so the auras could be a result of that misfiring.
I'd like to go back to the happy side of food.
Mm-hmm.
When we look at things, our eyes are not locked onto a target. They're constantly flickering around. So let's say the person is not eating the food on the left side. If he looks to the left, does he suddenly notice the food on the left side of the plate?
Yes, he will, because now so when you're looking here and the food, the plate of food is right in front of the person, can't see the left-hand side. If he moves his head, now his visual field has changed, right? Because now his focus is somewhere else. And so the food plate that was in the left visual field is now in his right visual field.
So wouldn't that ordinarily just happen?
Yes, so if they actually do move their head around that much, that will happen. Yes, but it's not, so blind spots are where you actually can't see things, right? This is different. So they can actually, their eyes can see things. Their retina is seeing that. Their earlier visual areas are seeing that, but they're not perceiving it. Yep. They do have their depth perception because their eyes are fine. Their vision is fine. It's just that their perception is off, right? So it's the recognition part of things, or the localization part of things.
So say a person is cutting someone's hair, would they have to constantly be moving?
Yes.
In order to make, because if they're just trying to see if this side is equal as this side, they'd have to keep
Yep.
moving to
Mm-hmm.
make it less.
Exactly.
Probably not a wise career choice.
They would definitely have to continue moving. So basically they have to put things on the on the side of the visual field that they can perceive to actually be able to interact with that part of their world. I don't think so, but I don't know that. I think it would be very dangerous, right? Yeah. So, I guess they would be able to wear like shifting prisms and then shift their visual field.
All right, I guess if people have some other questions, we'll if you could maybe stay around for a little bit longer. Sure. I just want to mention coming up, so next Friday is also known as Black Friday, and we have a tradition here of doing black holes on Black Friday. So Roy Williams will be up here to talk about black holes. He'll show you some of the latest pictures that we actually have of black holes. And then in December, we will have 2 different programs across 3 weeks. The first and third Fridays, we'll actually be running a program called Star Bethlehem. It's a movie that was actually, it turns out as a gentleman was an attorney, but he was also interested in astronomy, and he just took some software and dialed back to about the time of the birth of Jesus and said what was in the sky and how did he relate that to what was in Scripture. So that'll be on the first, and also we'll be repeating it on the third Friday. On the second Friday, Phil Cooper, who has done a number of programs on the space program, will be in to talk about the sort of super heavy rockets, the Saturn V, the Falcon Heavy, and some of the history of that, and now where we are going with these new rockets. Literally, will be taking us physically to Mars. So we will be going through mid-December. Also want to let you know that if you recall, or if you had heard, we did a sort of a haunting at the observatory just before Halloween. We are actually going to do a Holiday Horizons, sort of a holiday event on Saturday the 18th of so it's again sort of family oriented, and we'll do some interesting experiments, and of course hopefully the skies will permit. We'll do some nice viewing. But tonight I think we still have some great skies out there. Saturn is probably set at this point, but we should have Jupiter. The moon will still be out there, and we'll see what else we can find. So thank you, Dr. Karkhanis. Appreciate the really interesting talk. And any other questions, please feel free to bring them up. Otherwise, head on out to the scopes. The rule here is you cannot leave Kopernik until you look through a scope. All right, I'll track you down. So thanks again.